Hey guys, my name is IBM, and today I'm introducing another topic of AS. I think it's going to be force, density, and pressure. This is one of the easiest units, which I expect that students should be able to learn on their own from home. Okay, let's go and introduce the unit. So this is force, density, and pressure. I think this would be in maybe three to four lessons. I'll try my level best to give a lot of examples and where possible, but mostly there will be examples of IGCSE. Do not forget to watch the solved past paper questions under force, density, and pressure. Those will give you the best picture of what the Cambridge examiner is always going to be looking for in this unit. So let this be lesson one of force, density, and pressure. Normally, I prefer to start with density and pressure because I expect that density will take about 10 to 20 minutes, and that unit will be done. And the pressure may not also take long, but I know force, the concepts of force, because it involves force, center of gravity, moments, moment of a couple. It involves result, equilibrium, and so on and so forth. So I always prefer to start with the density and pressure. Then later on, I come back to force, moments, center of gravity, resultant force, equilibrium, and so on and so forth. Okay, so let's start with the density. Let's start with the density. What do we mean by density? Of course, the concepts of density are the same concepts you studied in IGCSE. Maybe that was year 10 or grade 9, depending on which schools you went to. So they are the same concepts we are going to talk about here, only that for AS level, I only include or I only talk about the concepts I expect that the teacher never mentioned in IGCSE, and that is the density of a mixture, and maybe simple or further complex examples are under density, because you don't expect an AS student to be just asked to calculate density from mass over volume. No. So I expect that a little bit more complex questions could appear at AS level, and those are the examples I would like to give at this level. Okay, so we know from IGCSE that density is the mass per unit volume. Because density is a scalar quantity, I can just define density as mass divided by volume. As simple as that. Many times students struggle to write a lot of things, and they end up missing a simple mark because they are trying to write long explanations. So density can just be defined as mass divided by volume. Of course, we know that mass is measured in kilograms and volume in meters cubed. Therefore, the units of density are going to be kilograms per meters cubed. That one you mentioned in IGCSE. So like I said, I'm so much interested in the concepts you never mentioned in IGCSE, especially the concept of the density of a mixture. So the density of a mixture of several substances many times students would think they would add the densities of each of the substance that makes up the mixture and then obtain the average, but it doesn't work that way. If you want to find the density of the mixture, then you must know the total mass of the mixture and the total volume of the mixture. So the density of a mixture is going to be total mass of a mixture divided by total volume of the mixture. In IGCSE, you also distinguished between scalars and vectors. Or you might have distinguished between scalars and vectors in the first unit of AS physics, that is physical quantities and units. And you might have mentioned density as one of the examples of scalars. And a scalar is a quantity which only has magnitude. So density is a scalar. We cannot talk about direction of density because it has no direction. So density is a scalar quantity because it has only magnitude. We can't tell the direction of density. So if you are given, for example, water and they tell you to find the density of water, you can't tell the direction of the density of water. So density is a scalar quantity. I will not give examples that you did in, I may not give examples that you did mostly in IGCSE, but I'll concentrate on examples that I expect will help you excel in equations under density for AS physics. Examples. In the first example, in a large container in an oil refinery, three oils of different densities are mixed. No chemical activity occurs. The mixture consists of 1,200 kilograms of oil of density 1,100 kilograms per meters cubed. 1,500 kilograms of oil, density 860 kilograms per meters cubed. 4,000 kilograms of oil of density 910 kilograms per meters cubed. Determine the density of the mixture. I have given an answer, so I just want to give you a clue. So to determine the density, we have just said that density of a mixture, the density of a mixture is equal to the total mass divided by the total volume. So total mass, I'll just add 1,200 plus 1,500 plus 4,000. But find total volume, I need the volume of each. Remember volume, because density is mass over volume, so volume is going to be mass divided by density. So for each of these, I will find its volume by dividing the mass by the density. So the total mass is going to be 1,200 plus 1,500 plus 4,000 divided by total volume. I would get the volume of each of these oils. So for the first one, the volume is mass over density. So that is 1,200 divided by the density, which is 1,100. That is the volume of the first oil plus. For the second oil, it is 800 and sorry, it is 1,000. It is 1,500 divided by 860. Then plus the last one is 4,000 divided by 910. So I'll try to simplify this with my calculator. So total mass is 1,200 plus 1,500 plus 4,000. So the total mass is 6,700. The total volume, have 1,200 divided by 1,100 plus 1,500 divided by 860 plus 4,000 divided by 910. So this is 7.23. So that is the total volume. So I'll just divide 6,700 divide by the answer. So this is giving me 926.6, which is approximately 927 kilograms per meters cubed as required. So that's how we find the density of the mixture. And I expect that this is the only examples that you never mention in IGCSE or in your year 10 or in your grade your grade um, your grade 9. A cube of copper has a mass of 240 grams. Each side of the cube is 3 centimeters long. Calculate the density of copper in grams per centimeter cubed and kilograms per meters cubed. So density is mass over volume. This is a cube. A cube has all sides equal. So the volume of the cube is going to be 3 times 3 times 3, which is going to be 27 centimeters cubed. The mass is that. So we want the answer initially in grams per centimeters cubed. So the density is going to be the mass divided by the volume, which will be 240 divided by the volume, which is 27 centimeters cubed. This is in grams. So 240 divided by 27. So this is 8.9. Or I can write 8.89. 8.89. This will be grams per centimeters cubed. So this will be the density of copper in grams per centimeters cubed. If you wanted it in kilograms per meters cubed, you have two ways of doing this. If you are very good at your IGCSE, you would multiply this by 1,000. But if you're not good at IGCSE, you can first convert each of these to the SI units. So the density, of course, the volume will be the side of the cube will be 3 times 10 to the power of minus 2 in meters. So the density is going to be equal to 240 times 10 to the power of minus 3 to change it to kilograms divided by the volume. The volume will be 3 times 10 to the power of minus 2, but this should be cubed. Because to 3 times 10 to the power of minus 2 times 3 times 10 to the power of minus 2 times 3 times 10 to the power of minus 2. In other words, I have to change the side to meters so that I can now multiply when it is in SI units. So this is going to be in kilograms and this is going to be in meters cubed. So I'll try to press my calculator again. So this gives me 8.9, or approximately it can be 8.890. That would be in kilograms per meters cubed. 8.890. Those are three significant figures in kilograms per meters cubed. So that would be the density in that case. Okay. The density of steel is 7,850 kilograms per meters cubed. Calculate the mass of a steel sphere of radius 0.15 meters. So we want mass of a steel sphere. A sphere, we must be knowing the volume of a sphere. So the volume of a sphere is given as 4 over 3 pi r cubed. That is the volume of a sphere. So that means density, which is mass divided by volume, is the same as saying that density is equal to the mass. Because the volume is 4 pi r cubed over 3, the 3 goes up, so it will be 3m divided by 4 pi r cubed. So I'm going to try and make r the subject here. So r is going to be the cube root, because r is to the power of 3, so r is going to be the cube root of 3m divided by 4 pi times rho. So I now just substitute in this equation. So it will be the cube root of 3 times the mass. I was finding the radius. We are finding the mass, not the radius. Sorry. We are finding the mass, not the radius. So since we are finding the mass, it means the mass is going to be equal to density times 4 pi r cubed divided by 3. So we just substitute in this equation. So the density is 7850 times 4/3 times pi times r, which is 0.15, and this is raised to power 3. So I'll check my calculator. 7850 times 4 divided by 3 times pi times 0.15 cubed. So I'm getting the mass as 110.9, or approximately 111 kilograms. So this is 111 kilograms. Oh, it is 110. Okay, so you can also try to verify that, but that's what I'm getting as the mass in that case. Okay, so I just try to use examples you never mentioned in IGCSE, examples which require some kind of extrapolation of knowledge. For example, I gave a cube, having known, or if you know that a cube has all sides equal, I showed you that you could find a volume from multiplying all the sides. Then I gave a sphere, just to remind you of the volume of a sphere, as 4/3 pi r cubed. That's the only thing you may not have mentioned in IGCSE. Okay, one more example. The density of water is 1.0 grams per centimeters cubed. I think this is a Cambridge question. You'll find it in my solved past paper questions, especially multiple choice, I think. And the density of glycerin is 1.3 grams per centimeters cubed. What is added to a measuring cylinder containing 40 centimeters cubed of glycerin, so that the density of the mixture is 1.1 grams per centimeters cubed? Assume that the mixing process does not change the total volume of the liquid. What is the volume of the water added? So we know that density of a mixture is the same as total mass divided by total volume. Okay, so I'm going to call, we have the density of water, I'll call it rho W, that is density of water. The density of glycerin, I'll call it rho G. For glycerin, water is added in a measuring cylinder containing 40 centimeters cubed of glycerin. So this is going to be the volume of glycerin, I'll call it Vg. And therefore I'll call the volume of water, I'll call it Vw. And we don't have any of the masses. Remember, mass is equal to density times volume. So it means I will say the mass of water is the density of water times the volume of water. That is the mass of water, which is going to be, density of water is 1.0 grams times the volume of water, which is not known. I'll call it Vw. Then the mass of glycerin is going to be the density of glycerin times the volume of glycerin. The density of glycerin is 1.3 times the volume of glycerin, which is given as 40. Here I'm not changing the units because I know if I have grams per centimeters cubed and centimeters, I don't need to change the units. I know that everything is in grams in that case. Okay, so it means total mass will be the sum of these two. So it means density of the mixture, which is given as 1.1 grams per centimeters cubed, is going to be the total mass, which is going to be the mass of water plus the mass of glycerin divided by total volume, which is the volume of water plus the volume of glycerin. So 1.1 is equal to the mass of water is 1.0 times VW plus the mass of glycerin is 1.3 times 40 divided by the volume of water is not known. I'll leave this as VW plus the volume of glycerin is known to be 40. So I'll just simplify by cross multiplying. So I have 1.1 VW plus 40 times 1.1, I think that is 44, plus 44 equals to VW plus 1.3 times 40, that is 52. So you collect like terms. I will take this one this side and I will take that one the other side. So I have 1.1 VW minus VW is equal to 52 minus 44. So so this gives us 0. I think this gives us 0.1 of VW, and the other side it gives us I think this is 8. 52 minus 45, I think that is 8. So it means 0.1 VW is equal to 8. So I divide by 0.1 by 0.1, which means VW is going to be 80 centimeters cubed. So it means the volume of water added is 80 centimeters cubed. So I have done a lot of, this is a multiple choice question. I've done a lot of algebra here, which is not necessary, but it's just for to give you confidence, especially if you're not a math student. So that is the end of, I think this should be the end of density. So if you know how to find the density of a mixture, you know how to deal with the mixtures, you know how to find cross-sectional areas of several shapes, volumes of several shapes, such as a cube, a cuboid, and a sphere, then you are good enough to go. That is density. Number two, let's also talk about pressure now. Let's talk about pressure. Having seen density, we should now talk about pressure. So what do we mean by pressure? Still, this was mentioned in IGCSE, only that I'll give a hint on concepts that I expect may not have been mentioned in IGCSE, and I also go further to a little bit more advanced concepts such as Upthrust and Archimedes Principle. So in IGCSE, I expect that you define the pressure as the normal force acting per unit area, or the force acting normally per unit area. So pressure is defined as the force acting normally per unit area. Unlike in a unit called deformation of solids, you might have seen that pressure, the units of pressure and Young modulus or stress were the same, but we defined stress as force acting per unit area, force per unit area. We didn't mind about if the force was acting normal or perpendicular. So normal in this case is meaning perpendicular. This means perpendicular. That is at right angles. So pressure is the force acting perpendicularly per unit area, normally per unit area, or at right angles to a unit area, that is pressure. So sometimes you may just define the pressure by writing a simple formula that pressure is the normal force over area. When you say normal force, you are actually emphasizing that the force acts perpendicular to the surface area. It's not just force over area, that will be stress maybe. So of course, mathematically in IGCS you were writing P as F over area, And because we know that force is measured in newtons, and area is measured in meters squared, in IGCSE we were saying that the units of pressure are newtons per meter squared, which is the same as the Pascal. In memory of Pascal, the first person to establish the relationship due to the relationship of pressure and depth, or pressure at any point in a liquid, where he stated that pressure acts equal in all directions in a fluid. That was Pascal's principle. However, from the first unit called physical quantities and units, you could also express the units of pressure, which is the Pascal, in what we call base units. So, because we know that force could also be mass times acceleration, the units of force could be for mass, which is kilograms, and for acceleration, which is meters per second squared. And the units of meter of area are already meters squared. So it means the units for pressure would be the units for force, which is kilogram meters per second squared, divided by area, which is meters squared, which simplifies to kilograms. M divided by m squared becomes m power minus 1 s power minus 2. So the examiner may ask you to express the Pascal in base units. So the Pascal in base units will be that quantity there, kilogram per meter per second squared. That will be the Pascal in base units, or Newton per meter squared in base units. Okay. So I want you to also recall from IGCSE that the smaller the cross-sectional area, the higher the pressure, because pressure is inversely proportional to cross-sectional area. The larger the cross-sectional area, the smaller the pressure. That you mentioned in IGCSE. You also mentioned that pressure in fluids, call them gases and liquids, does not depend on cross-sectional area. And we can prove this. Pressure in fluids or pressure in liquids and gases does not depend on cross-sectional area. I think this you might have not proved, but we can prove it right now. So pressure in fluids depends entirely on depth, as we are going to see. Pressure in fluids does not depend on cross-sectional area, even though pressure is the normal force acting per unit area. Pressure in fluids does not depend on the cross-sectional area, but it depends on depth. In fact, pressure in fluids increases when the depth increases. Liquid pressure increases with depth. Likewise, atmospheric pressure decreases with increasing altitude, that is, increasing height. Of course, if the height increases, the depth of the air column above a given surface becomes smaller. That's why that's why atmospheric pressure decreases with increasing altitude. Because if this is the reference point of the clouds, for example, and this is this Earth's surface, the pressure at this point here is going to be higher than the pressure at this point here, because the atmospheric pressure here is due to the air column above this point, which means the H is bigger. The atmospheric pressure at this point is due to the air column above this point, which means the H here is smaller. So if this is H1 and H2, you see that H1 is greater than H2. So atmospheric pressure at this point here is lower than atmospheric pressure at this point here. That's why we say atmospheric pressure decreases with increasing altitude or height above sea level. Okay, let's explore liquid pressure then. So if you pour a liquid into a container, or a container which has several shapes, but all shapes open to the atmosphere, the liquid will flow through. Even if I pour it from, say, this end here, the liquid will flow through, and at the end of it all, the liquid in all the shapes will settle at the same level. What does that mean? The pressure at any point is therefore acting equally and in all directions, which is making the liquid to flow into this and then rest at the same level, where if it is open to the atmosphere, in each of these open tubes, we consider there to be atmospheric pressure. So Pressure at any point acts equally in all directions. And it is not depending on the shape of the object. You mentioned it, you must have mentioned that in IGCSE. It doesn't depend on the shape of the object. It just depends on the depth. Pressure in liquids depends on the depth. That's why in all the containers, in all the shapes we have here, the liquid is settling at the same depth. So for a liquid of a fluid at rest, the pressure at any point acts equally in all directions in the first place. Number two, the pressure increases with the depth. We want to verify this mathematically and show that pressure does not depend on cross-sectional area. So let's consider a point, for example, a point at the bottom of this container, let's say at the same level with this container, let's say at this point here. The point at the bottom of this container, which is in a fluid whose density is 0. Let's say it is at a depth h below the point we are considering is at a depth h below the container, or it is at a depth h below the surface of a liquid in the container. So the pressure due to the liquid is caused by the weight of the liquid, the weight of the column of the liquid, which is above that small point, above a small area at that depth. So if we want the pressure expressed, the pressure exerted at the bottom of this container, it is the same as the pressure due to the liquid column caused by the weight of the column of the liquid above that small area at that depth. So a submerged object is of course expected to displace its own weight. So we expect that the weight of this object here is the same as the weight of the liquid it displaces. And remember, weight is equal to m times g. And of course, we also know that the mass is equal to density times volume. So it means the weight of the liquid displaced could be given as density times volume times g. Since the object displaces its own weight, then it means the volume of the liquid displaced is the same as the volume of this object. The volume of the object is going to be the cross-sectional area A times the depth or the height h. So it means the weight is going to be density. Where there is volume, I will put cross-sectional area times height, that is volume, then times g. So the weight, of course, weight is a force, and by definition of pressure as force over cross-sectional area, then it means we are going to have density times A times h times g over cross-sectional area, and area cancels out. Therefore, we say pressure in a liquid is going to be equal to density times g times h. Therefore, it is not depending on the cross-sectional area. That's why we say pressure due to a liquid simply increases with the depth. Pressure in the liquid increases with depth. Okay, so if we consider a point at a depth h below the surface of a liquid in a container, the pressure due to the liquid is caused by the weight of the column of the liquid above a small area at the depth. A submerged object displaces a liquid of its own weight. So the object we have considered displaces its own weight. So the weight of the liquid displaced by a submerged object is the same as the weight of the object itself. And weight of the liquid column which is displaced is going to be mg. And of course, we know mass is density times volume, but the volume of the object is the same as the volume of the liquid displaced, which will be a cross-sectional area of the object times the height of the object, or times the depth. So if we use the definition of pressure as force over area, the force is going to be the weight of the liquid displaced, or the weight of the liquid column, then divide by the area. So we just substitute and the area cancels out. So we conclude by saying that pressure due to a liquid or liquid pressure is given by density times G times H. This one is read as rho. Rho. Many students fail to write rho. So that is pressure in liquids or liquid pressure. It depends on the density of the liquid and the depth. Of course, considering acceleration of free fall a constant, or acceleration due to gravity a constant. Okay, so you should be able to show this because the examiner will ask you to show this and will give that 3 marks. Show that pressure due to a liquid is equal to density times H times G. You should be able to show that because this is AS level. A few things we need to note from what I've just mentioned. So normally the equation for liquid pressure is written as a change in pressure equals to rho g change in height because this formula calculates the difference in the pressure between the top and the bottom of the object. You notice that H was the depth of the object in the liquid, but at the bottom, at the top of the object, there is also atmospheric pressure, and at the bottom of the object, there is atmospheric pressure plus the pressure due to that depth, which means what we have just obtained previously is a difference in the pressure between the top of the object and the bottom of the object. And by the way, in IGCSE, you also mentioned that pressure is a scalar quantity. Sometimes people think atmospheric pressure is a vector quantity because they believe atmospheric pressure acts vertically downwards, which is not true. In IGCSE, you must have performed a simple experiment where you poured water in a glass and covered it with a card, and you turned the glass upside down and the water remained in the glass simply because atmospheric pressure acts in all directions. So then the fluid density rho is always assumed to be constant, but sometimes it may not be constant, especially if it is air. The density of air close to the Earth's surface is not the same as the density of air as you go far away from the Earth's surface. Close to the Earth's surface, the density of air is approximately 1.2 kilograms per meters cubed. But as you go far away from the Earth's surface, the density of air may decrease slightly. However, whenever we use pressure equals to rho gh, we are actually assuming that the density rho is constant. However, if it varies linearly, we may find the average density before we do the calculation. Okay, number 4, the fluid pressure P is equal, that is acting in all directions at all points, having the same depth, independent of the shape of the container. That's why in the first diagram, we saw that even if we have different shapes of the container, the liquid, if we pour the liquid in here, it will settle at the same level, independent of the shape of the container, but it will only depend on the depth. So the fluid pressure is equal, acting in all directions at all points, having the same depth, independent of the shape of the container. So if I want to find the pressure at this point here, it will be the same pressure at this point here, it will be the same pressure at this point here, because they will all be at the same depth relative to the position to the surface of the liquid. So pressure at equal depths is the same, independent of the shape of the container. Pressure at equal depths is the same, independent of the shape of the container. Okay. It should also be remembered that the actual pressure at the depth h in an open fluid would be given by, if the fluid is open, we have total pressure at the depth h, which we calculated in the previous slide, which will be the fluid pressure plus the atmospheric pressure at the fluid surface. So if the object is submerged in the liquid, like we have seen in the example, and I say I want the pressure on top of this object here. If the container is open, there is atmospheric pressure here. There's atmospheric pressure, and then there's pressure due to this height. So it means total pressure on top of this object will be atmospheric pressure plus pressure due to the height h, which is h rho g. Therefore, the total pressure is going to always be given by the pressure due to the depth plus the atmospheric pressure. That is how we find total pressure at a given point in a liquid. If um, if it is an open fluid, or if the object is open, We get the pressure due to the fluid plus the atmospheric pressure in most cases. Okay, so that is all I could say about liquid pressure for now. Do not forget to watch the solved past paper questions. You'll gain more confidence in using these expressions. Let's also talk about gas pressure. So in IGCSE, you talked about a barometer, a device that you use to measure gas pressure. And your teacher must have told you that experiments show that every time a liquid or mercury was poured into such a barometer and the vertical height was measured, I think every time this vertical height was approximately, I think it was always approximately 76 centimeters of mercury. It was always 76 centimeters of mercury every time the atmospheric pressure was measured, or every time the vertical height was measured. And your teacher must have also mentioned at that point that therefore it meant that atmospheric pressure was always 76 centimeters of mercury. So if we consider this demonstration with a barometer, where mercury is placed in a tube and then it is inverted, of course the mercury falls out of the tube until it stops at a point where the pressure here, where the atmospheric pressure pushing this liquid balances with the pressure due to the height in the liquid. So the atmospheric pressure which is pushing the liquid cannot push it any further. It balances with the pressure due to the height of the liquid in the tube, which height is 76 centimeters of mercury. So the pressure which is at this point is atmospheric pressure. If it can't push the liquid any further into the tube, it means the atmospheric pressure outside is balancing with the pressure due to this height. So if we can measure the height, if we can measure this height, and we know the density of mercury, I think the density of mercury is about 13,600, I think. So if we can measure the height, and our experiments have shown that is approximately 76 centimeters mercury, then we can predict atmospheric pressure. So here it is a vacuum. Of course, the mercury does not leave anything out there, so this will create a vacuum. You mentioned that in IGCSE. So let's find the atmospheric pressure P2 is going to be the same as the pressure due to this height h, because there is no more mercury coming out of the tube. So it is going to be h density times g. So h is 76 centimeters of mercury. So I will say 76 times 10 to the power of minus 2 of mercury. So the density of mercury, I think, is 13,600. Then times g, which is 9.81. I'm trying to find the atmospheric pressure. So 76 exponent minus 2 times 13,600 times 9.81. So this is 1.01 times 10 to the power of 1, 2, 3, 4, 5. Power 5 pascals. So it appears as if atmospheric pressure is that, I said 13,600 is the density of mercury, because normally here we have mercury. That's what you mentioned in IGCSE. So of course, to measure gas pressure, you use the barometer. That is for IGCSE. I just wanted to help you note something you'll always remember, or you'll always use in AS level, that the mean pressure of the atmosphere at sea level is 1,100 kilopascals. I think this is 1,100. 1,0,1,0,0. One 101 kilopascals. I think that is true. So it is 101 kilopascals. That is the mean atmospheric pressure. Of course, there is a question in paper 1 or paper 2 sometimes which asks you to state some estimates. And we have also mentioned that atmospheric pressure decreases with increase in height above sea level. I think I've explained this, that if the height above sea level increases, the atmospheric pressure decreases. I gave a simple illustration. Let's say this is a reference point, which is the clouds, and this is the Earth's surface. And I'm saying that the pressure at point A compared to the pressure at point B, I say the height of the air column from, say, the clouds to the point we are considering, the height is H1. And the height of the air column from the clouds, say, to the Earth's surface at a high altitude, this is H2. The pressure at A is going to be H1 times density times G. And the pressure at B is going to be H2 times density times G. But note that H1 is greater than H2, which means the pressure at A is greater than the pressure at B. So atmospheric pressure therefore decreases with increase in height above sea level. The higher you go, the smaller the atmospheric pressure. Okay, we are still talking about gas pressure. Let's consider another situation where a gas or any other substance, probably gas, is trapped into a container, but there is a liquid on the other side, and the other side is open to the atmosphere. So for the open atmosphere, the pressure there is always atmospheric pressure. If one end of the container is opened, the pressure on that open end is always the atmospheric pressure. So this side the gas is trapped, and we just look at the height of the liquids on both arms of this. This is what you call the manometer. You call this a manometer in IGCSE. So you notice that the liquid level on the left-hand side of the manometer is lower than the liquid level on the right-hand side of the manometer, which means the pressure, on the other side, pressure 2, is greater than pressure 1. The gas on the left-hand side is pushing the liquid in the manometer to rise towards the end of the atmosphere, towards the end of the atmospheric pressure, which means the pressure of the gas is greater than the pressure of the atmosphere, or the atmospheric pressure. If the liquid on the left-hand side was to be higher, the liquid column on the left-hand side was to be higher than the liquid column on the right-hand side, then we would say the atmospheric pressure is greater than the pressure of the gas. But this time, it is not the case. So if I want to find the pressure of the gas, or the pressure P2, it will therefore be the pressure due to the atmosphere plus this rise in the liquid level is the excess pressure of the gas above the atmosphere. Therefore, the pressure P2 would be equal to the atmospheric pressure plus the pressure due to the height of the liquid column on the right-hand side. In other words, to find the atmospheric pressure, it is the same as getting the pressure of the gas minus the excess pressure, which is the pressure due to the height h, or the difference in the height of the liquid column. That is how we find our pressure of a gas using a manometer. Further examples on that. So let's consider the first situation where we have a gas trapped in a container, but the end of the container has been closed and we have a vacuum there. So we notice that the gas is pushing the liquid on this side to rise. So it's like the pressure of the gas is simply going to be equal to the pressure due to this height, because this side is closed. This side is closed. So the gas will push the liquid until it cannot push it any further. In other words, the pressure due to this height of the liquid balances with the pressure of the gas the other side. And because it is closed, therefore we can just simply say that the pressure of the gas is equal to the pressure due to the height of the liquid column, simply because our U-tube is closed. But if the U-tube is opened, it is not going to be the same case. If the manometer or the U-tube is opened, this is an open U-tube, it is opened. It means if the liquid, and we notice here that the liquid is being pushed to raise this side, so the liquid column is on the left-hand side is higher than on the right-hand side, which means the pressure of the atmosphere is pushing against the pressure of the gas. So here the pressure of the atmosphere is greater than the pressure of the gas. That's why the liquid rises on the side of the gas. So because the pressure of the atmosphere is greater than the pressure of the gas, it means to get the pressure of the gas, we must get the pressure of the atmosphere minus the excess pressure. That's why the pressure of the gas is going to be the atmospheric pressure minus the pressure of the atmosphere. Atmospheric pressure minus the pressure due to the height h, which here has been given as 4 centimeters. And number 3, let's say it is the other way around. We have an open tube here, and we notice that the liquid is raising onto the side, or is being pushed through a height say 0.5 centimeters onto the side of the open atmosphere. So it means the pressure of the gas is greater. In this case, the pressure of the gas is going to be greater than the atmospheric pressure. So it means to find the pressure of the gas, I must find the pressure of the atmosphere plus the excess pressure due to that height. So let us assume, let's try to find these pressures, because we know that at this level, we know that the density of water, assuming water was used into this container instead of mercury, assuming that the density of water is known to be equal to 1000 kilograms per meters cubed. You should be knowing this at this point. So it means in this case that the pressure of the gas would be equal to, the height is 2 centimeters, 2 times 10 to the power of minus 2. Density is 1000, G is 9.81. So in this case, the pressure of the gas will be 9.81 times 2 exponent minus 2 times 1000. So here the pressure of the gas will be 196.2 pascals. And in the second case, of course, we already know atmospheric pressure. We know that atmospheric pressure is approximately 101,000 pascals. So here the pressure of the gas is going to be 101,000 minus the pressure to the height h, which will be 4 times 10 to the power of minus 2. The density is 1000 times 9.81. So this is 101,000 minus. So this becomes 1,00607 or 08. Approximately it is 1,00600 pascals. That will be the pressure of the gas. Then in this case, the pressure of the gas is going to be atmospheric pressure, which is 101,000 plus the pressure with that height, which is going to be 0.5 times 10 to the power of minus 2, then times 1000 times 9.81. So 0.5 exponent minus 2 times 1000 times 9.81, then plus 101,000. So this is 101,049 pascals. So this is almost approximately the same, because this is very, very small. Okay, so that's how we find the pressure. Look at the side of the manometer or of the YouTube, where the liquid column in the YouTube rises. If the liquid column rises to the left, where we have the gas, it means the pressure of the gas is lower. If the liquid column rises to the right, where we have the atmospheric pressure, it means the atmospheric pressure is lower than the pressure of the gas. So to find the pressure of the gas, we must get the atmospheric pressure plus the pressure due to that excess height. You'll be finding such questions in your exams, do not forget to visit the solved past paper questions. Note that, I think I should wrap off this so that the note is visible. Note that when the level of the liquid on the side of the tube next to the gas, when the level of the liquid on the side of the tube next to the gas is lower than on the side open to the atmosphere, the pressure of the gas is above atmospheric pressure and vice versa. When the level of the liquid on the side of the tube next to the gas is lower, it means the pressure of the gas is greater or is above atmospheric pressure, and vice versa. That is, the reverse is also true. Okay, so that is how you should be able to calculate the pressure due to a gas, or it could be any other thing which could cause a change in pressure. The figure above shows manometers used to measure the pressure of the gas. The liquid used in the manometer is water of density 1000. Calculate the pressure difference between the gas inside the pipe and the atmospheric pressure in Roman 2 and Roman 3. I think that one I've already calculated that. When they say pressure difference, you just find they want just the pressure due to the height, delta H times density times G. In Roman 2, H was, I think, 4 centimeters. In Roman 3, H was 0.5 centimeters. So you just substitute in that equation, find the pressure difference in each case. I will not do that. Then deduce the pressure of the gas in each case. We have calculated the pressure of the gas in each of the cases in the previous slide. Then we can use the concepts of pressure to compare differences. So let's see how we compare densities. Let's see how we compare densities of two liquids using the concepts of pressure. Remember, according to Pascal's principle, the pressure at equal depth is the same and acts equal in all directions. So let's consider two liquids which do not mix. We have oil and water. And oil is poured on one side of the U-tube and water is on the other side. Let's say the density of oil, I'll say the density of oil, let it be rho O or rho naught, but that is rho O. And the density of water, I'm going to call it rho W. So we want to compare or to obtain the relationship between density of oil and density of water when these two liquids are poured in the same U-tube. Remember, they do not mix. However, remember that the pressure at the same level in the same liquid is the same. So if I consider water at this point here, the pressure here is the same as the pressure here at the same level in the same liquid if I consider water. So the pressure at X is the same as the pressure at Y if X and Y are on the same level. If X and Y are on the same level, pressure at the same level in the same liquid is the same because pressure acts equally in all directions. And if that is true, therefore, if that is true, the pressure at the same level in the same liquid is the same. So pressure at X is the same as pressure at Y. That is due to the liquid, which is water. But what is the pressure at X? And what is the pressure at Y? The pressure at X, because the container is opened, we have atmospheric pressure here. And we have pressure due to this height here, which is going to be given by density, because pressure due to the height is density times G times the difference in height H. So the height is Hx. So pressure above point X is going to be the atmospheric pressure plus Hx times the density of the oil times G. Then pressure at this point, it is also open to the atmosphere. So here we have atmospheric pressure. So we have pressure due to the atmosphere, then plus pressure due to this height, which is Hy. Therefore, we shall say pressure at point Y is going to be atmospheric pressure plus pressure due to the height Y. So of course, atmospheric pressure will cancel out and G will also cancel out. So I remain with Hx times density of oil equals to Hy times the density of the water. So that means if I divide both sides and rearrange the equation, I have that density of oil over density of water is equal to Hy over Hx. So that is the relationship between between density and height using the concepts of pressure or using the understanding of pressure in liquids. Let me use a simple question from past papers for us to be able to understand this. So here I have a YouTube. I think this is one of the past paper questions. I don't know whether this is 2021. A YouTube has one arm of area of cross section A. So area this side, one side is A. So this could be A and the other side could be 4A. The tube contains water of density 1000 kilograms and oil 850 kilograms per meters cubed. So here we have density is 850 and density of water is 1000. Please, you should be noting the density of water because sometimes you are asked to make estimates. The column of oil on top of the water in the left-hand arm is of length 30 centimeters. What is the difference in height, x, between the levels in the two arms of the tube? Remember I have said the pressure at the same level in the same liquid is equal. So I'm going to look for the same level then. So it means the pressure here in water is the same as the pressure here due to water. Same level in the same liquid. So what is this height here? This height here is going to be 30 minus x. That is 30 minus x. So pressure on the left hand side is going to be pressure due to the atmosphere because it's an open container plus the pressure due to the oil or the excess pressure due to the oil should be equal to, that is the pressure at this point here, should be the same as the pressure on the other side, which is going to be the pressure due to the atmosphere plus the pressure due to the water, that side. So atmospheric pressure cancels out. So the pressure at this point here due to the height or due to the depth of the oil is going to be, remember, pressure due to the liquid is equal to H density times G. So this will be H, I will not change the units, so it will be 30 centimeters times, that is H, times the density of the oil, which is 850. There's a reason as to why I'm not changing the units because I'm equating, so the units centimeters can cancel out. So it's equal to 850, that is kilograms per meters cubed, should be equal to, so there is a G somewhere, so that is times G, should be equal to the pressure due to the water of height 30 minus x. So the height is 30 minus x, then times 1000, then times G. So G cancels out. So you remain with 30 centimeters times 850 equals to 30 minus x times 1000. Okay, I'm trying to find x because the question is what is the difference in height, x, between the levels in the tube, arms of the, in the tube, in the two arms of the tube. So I want to find x. So I'm going to just make x the subject. So I'll first divide 30 times 850. 30 times 850. So you have that 30 minus x is equal to 30 times 850. Remember, this is still centimeters. Divide by 1000. I've ignored the units of 850 and 1000 because they are the same, kilograms per meters cubed. These ones are going to cancel out. So I only remain with the units of centimeters. So this is going to give us divide by 1000. So this gives us 25.5 centimeters. So 30 minus x is 25.5. So what is x? X is going to be 30 minus 25.5, which I think gives us 4.5. So the difference in height x is going to be 4.5 centimeters. You can try to follow the same. So I have used the concepts of comparing pressure at the same level using Pascal's principle. Pressure in the same liquid at the same level is equal because it acts equally and in all directions. That is according to Pascal's principle. Okay, so here I have a lot of self-checks for you to practice. I'll give a hint where possible. Estimate the pressure you exert on the floor when you stand on both feet. So you can try, you have first of all to estimate the area of your feet. You can assume that your feet are rectangular. And if you assume that your feet are rectangular, you'll find the area of the rectangle, then you estimate your mass. Uh, if your mass is 60 kilograms, for example, then it means you can find your weight. The weight is going to be the force, which is mg. So your weight will be 60 times 9.81. Then you estimate your weight. You put your feet together and you try to estimate the length and the width. I will use mine. I think my feet is long, about 20 centimeters. 20 by 10. So the area of my feet, I'm using my feet, assuming they are rectangular in nature. The area could be approximately 10 centimeters by 20 centimeters, or 10 is 0.1 by 0.2 meters, which gives you an area of about 0.02 meters squared. So I can now estimate the pressure I exert. So pressure is going to be force over area, and therefore the force is 60 times 9.81 divided by 0.02, which is approximately 29430. Because this is an estimate, you can give it to one significant figure because it's just an estimate. So I can say approximately 30000. 1, 2, 3, 4. 1, 2, 3, 4. So because it's an estimate, I can just write one significant figure. You can't write many significant figures for an estimate. That's not acceptable. Maximum 2 significant figures for an estimate. Estimate the height and the height of the atmosphere. If atmospheric density at the Earth's surface is 1.29 kilograms per meters cubed, atmospheric pressure is 101 kilopascals. So here just use pressure equals H rho G. You have the pressure, they've given the density, G is 9.81. You should be able to find H. Calculate the pressure due to the water on the bottom of a swimming pool if the depth of water in the pool varies between 0.8 meters and 2.4 meters. Density of water is 1000. If the atmospheric pressure is 101 kilopascals, calculate the maximum total pressure at the bottom of the pool. Of course, for the maximum, you'll just sum up. You'll just get the pressure due to the liquid of the water, and you find the pressure due to plus the pressure due to the atmosphere. But here they say the pressure due to the water on the bottom of the swimming pool. If the depth of water in the pool varies, so the depth is not uniform. So since the depth is not uniform, then we can find the average depth. We can find the average depth because the depth of water in the pool varies between 0.8 and 2.4. So the average depth is going to be the sum of these two divided by 2. So it is 0.8 plus 2.4 divided by 2. So the average depth is 1.6 meters. So the pressure due to that depth is going to be H rho G, which is going to be 1.6 times 1000 times 9.81. So that is going to be the pressure due to the water. 1.6 times 9.81 times 1000. So it is 15,696 or approximately 16,000 pascals. So if I want to find the maximum total pressure, so pressure total is going to be the pressure due to the water plus the atmospheric pressure. So it's 101,000 plus 16,000. So 101,000 plus 16. So this is approximately 117,000 pascals. You can check that. Capture the excess pressure over atmospheric at a point 1.2 meters below the surface of the water in a swimming pool. The density of water is this. So here you just use, they want excess pressure over atmospheric. That is just a difference in pressure, which is going to be difference in height h times density times g. So they have given you the depth. They've given you, we know the density, we know g. You just substitute. Here is an exercise. I'll still give a hint, just a hint. Calculate the difference in blood pressure between the top of the head and the soles of the feet of a student 1.3 meters tall standing upright. Take the density of blood as that. So we want the difference in the blood pressure. Difference in blood pressure will be equal to density times G times difference in height, where delta H or difference in height is 1.3. I think that one is direct. A giant squid of length 20 meters is vertical in seawater with the top of the squid at a depth of 80 meters. The density of seawater is 1050 kilograms per meter squared. What is the difference in the pressure between the top and the bottom of the squid? So because the length of the squid is 20 meters, with the top of the squid being at depth of 8, so this, I know this will confuse a lot of students. So let me draw this as the water. So let this be the squid. And they are saying the top of the squid is at a depth of 80 meters. So this is 80 meters, assuming this is the surface. And they're saying the length of the squid is 20 meters. So they want you to find the difference in pressure between the top and the bottom. So I just want to give you a hint that you to find the pressure on the top, ignoring the atmospheric pressure on the top, I'll call it P1, will be equal to H1 times density times G, which is going to be 8 times the density times G. To find the pressure at the bottom, you'll get the height H2, which is this height here from the top of the liquid level, H2. So pressure P2 is going to be H2 times density times G, which is going to be 20 plus 8, which is 28 times density times G. So if they want the difference in the pressure between the top of the object and the bottom, difference in pressure will be P2 minus P1, which is the same as saying H2 minus H1 multiplied by density times G times height, which is the same as, because H2 minus H1 is just 20, so it will be the same as just the length of the squid, which will be 20 times density times G. So I'm saying that the difference in the pressure here will just be the length of the squid times density times G, which will be 20 uh, times the density, which is 1050 times 9.81. I know people will use 8, others will use 8 plus 20, but we just want the pressure between the top of this object and the pressure at the bottom. So you can find the pressure on the top using the depth of the top from the level surface of the liquid, and you can find the pressure at the bottom using the height of the liquid column up at the bottom of the object. Then you subtract, which is the same as just multiplying the length of the squid times density times G. And I think that is correct. The density of air on the earth decreases almost linearly from 1.22 to 0.74. So if it decreases linear, then the average density is the best. So it will be 1. Average density will be 1.22 plus 0.74 divided by 2, because the decrease is linear. So the average density is 0.98 kilograms per meters cubed. Atmospheric pressure at the Earth's surface on a particular day is 100,000 pascals. The value of G between the Earth's surface and an altitude of 5,000 meters can be considered to have a constant value, so G is 9.7. What would be the atmospheric pressure at an altitude of 5,000 meters? So the pressure at sea level is this. So if it is an altitude of 5,000 meters, how high have we gone? By what amount has the pressure decreased? So the change in the pressure is going to be equal to the change in the height times density times G. The change in the height, we have moved upwards through a height of 5,000. So this will be 5,000 times the average density, which is 0.98, then times G, which is 9.7. So 5,000 times 0.98 times 9.81. Oh, sorry, 9.7, not 9.81. 5,000 times 0.98 times 9.7. Here we're using G as 9.7, so this gives us 47530, which is approximately 48000 pascals. So that is the difference in, or the change in pressure. So we remember we are moving upward. So the pressure at the surface at sea level is 100,000. So if we go high, it decreases or it changes by this amount. So the pressure we're talking about is going to be 100,000 minus 48,000, which I think gives us that answer there, 52,000 pascals. Okay, let's also talk about upthrust and buoyancy. Upthrust and buoyancy. So what do we mean by upthrust? So when somebody talks about upthrust, of course, up is vertically upwards, and it's like a thrust means force. Thrust means force. So what do we mean by upthrust? So in this area, we're going to learn just, of course, you might have mentioned upthrust in IGCSE and buoyancy, but you may not have mentioned Archimedes principle. So we want to explore, we want to arrive at what we call Archimedes principle. So what happens when a body is submerged in a liquid? When an object is immersed in a fluid, it appears to weigh less than when in a vacuum. That's why timber, for example, can easily be carried in water than in air. You can try this in a swimming pool. Try to lift an object when you are in a swimming pool and try to lift it when you are in air. An object weighs less than when in air, I mean in water or in a liquid than it would weigh when it is in a swimming pool. It is easier, therefore, to lift heavy objects underwater than when they are out of the water because there is a force in water which acts vertically upwards, and that force is going to be called upthrust. It's like this force reduces the actual weight or makes the weight of the object to be a little bit less. Why is that pressure? Why is that force there? Remember we said when an object is submerged in a fluid, there is a pressure on top due to the liquid, but there is also pressure at the bottom due to the same liquid. And we have said that pressure due to a liquid increases with the depth. What does that mean? The pressure at the bottom of the liquid, is higher than the pressure at the top of the object. The pressure on top of the object is less than the pressure at the bottom of the object. And because pressure equals to force times area, force over area, it means force is equal to pressure times area. Because the pressure at the bottom is greater, it means the force upwards at the bottom is going to be greater than the force on the top of the object. And this difference in force is what we are going to call the upthrust. Is the what is going to act as the upward force on the object. So upthrust is an upward force that acts on an object immersed in a fluid. A fluid could be a liquid or a gas. That upward force which acts on an object immersed in a fluid is what we call upthrust. I'm saying this force makes the object to weigh less than its usual weight in air or in a vacuum. Therefore, the upthrust is like the difference the difference between the weight of the object if it is weighed in air or in a liquid, in a vacuum, minus the weight of the object, the weight in a fluid or the weight in a liquid. So the upthrust of a substance is the weight in air or in a vacuum minus the weight in the liquid. We call it the apparent weight. So upthrust occurs because the pressure in a fluid increases with depth. The deeper the object goes, the higher the pressure. So it means the pressure on the object at the bottom is greater than the pressure of the object at the top. This causes an upward force on the object. So because pressure increases with depth, the pressure on the bottom of the object is greater than the pressure on the top of the object. And the force is pressure times area. So the force at the bottom of the object is always greater than the force at the top of the object. The difference in this force is what we are going to call the upthrust. So this means the pressure at the lower surface of a submerged object is greater than the pressure at its upper surface. So that difference in pressure results into a difference in force on top and the bottom of the object. So thus, the force at the bottom is greater than the force at the top, giving a resultant upward force which we call the upthrust. The examiner will ask you to describe the origin of upthrust. Describe the origin of the upthrust force on the object. Upthrust is due to difference in the pressure on the top and the bottom of the object. Pressure in fluids increases with depth. The pressure at the bottom is greater than the pressure at the top. Therefore, the force at the bottom is greater than the force at the top. The difference in pressure in force between the top and the bottom is the resultant force on the object, which we call the upthrust, whenever the object is submerged. So that is the origin of upthrust, difference in pressure between the top and the bottom of a submerged object. Okay, we're still exploring upthrust and Archimedes principle. So let's consider an object which has been fully submerged. So the pressure at the top of the object is going to be given by the density of the liquid times the height on the top of the object, we are calling it h1, then times g. That means the force exerted on top of the object is going to be equal to, when I make from pressure equals to force over area, it means the force is pressure times area. So the force is going to be the pressure, which I've called P1, times the area, which is the same as H1G times A. And this acts downwards on top of the cylinder, as shown in that diagram. Then let's consider the bottom of the cylinder. Pressure at the bottom of the cylinder is given by density times the depth of the liquid, which is H2 from the surface of the liquid, then times G, which means that the force at the bottom of the cylinder is going to be equal to rho H2G times A. Of course, this force acts on the cylinder vertically upwards to the liquid. So we notice that because H2 is bigger than H1, then F2 is greater than F1. Therefore, F2 is greater than F1. So the resultant force is the upthrust. The resultant of these two forces is going to be the upthrust. We shall always use letter capital U for the upthrust. It's going to be the upthrust on the cylinder. So the upthrust is going to be the difference between these two forces, F2 minus F1. If we take back the quantities, we have F1 as H rho 1, rho H1 GA, and F2 as H as rho H2 GA. So if we bring that back, it's going to be actually P2 minus P1. Of course, this is the same as cross-sectional area times difference in pressure. So sometimes we shall calculate upthrust from either difference in the force at the bottom of the cylinder of the object and the top, or we shall calculate from cross-sectional area times difference in pressure, or if we go further and substitute the quantities here, rho H2GA minus rho H1GA, when you factor out the common factor, it will be cross-sectional area rho G, H2 minus H1. Therefore, sometimes we shall calculate upthrust from cross-sectional area times density times G times H. Of course, we notice that rho G times change in H is just difference in pressure. Difference in pressure is the same as rho G difference in height. That is H2 minus H1. So that's how we shall be calculating what we call upthrust. Some of the things we need to note here. The more the object is lowered into the liquid, the bigger the volume of water displaced and the bigger the upthrust. If the object was partially submerged, for example, the object was just submerged in that case, if we push it further, the upthrust increases. But when the object is fully submerged, the upthrust does not increase any further, it remains constant. Why is it that when we push it deeper, the upthrust increases? Because the depth of the object increases. That means H2 increases. So it means the pressure at the bottom increases when more of the object is submerged. So the upthrust increases. But when the object is fully submerged, the total pressure on the top of the object increases, the total pressure on the bottom of the object increases, and they increase uniformly, but the difference between the two remains the same. So when the object is fully submerged, the upthrust remains constant and the volume of water displaced is equal to the volume of the object. So if the object is fully submerged, the upthrust remains constant. Please, you should watch the solved past paper questions to understand the application of this concept in calculations. So when the object is fully submerged, the upthrust remains constant because the H2 minus H1 is a constant value in this case. But in the previous case, before the object is fully submerged, H2 goes on increasing as more of it is submerged because H2 is maximum when the whole of it is submerged. But if more of it is being submerged, H2 is increasing and it becomes maximum when the whole object is submerged. So I am saying when the object is fully submerged, the upthrust remains constant in that case. And the volume of the water it displaces is going to be equal to, the volume of the water displaced is going to be the same as the volume of the object itself. Okay, let's now understand Archimedes' principle, having understood what we mean by upthrust. So we have already seen that upthrust is the difference in the force on the top and the bottom of the object. That is, upthrust is equal to F2 minus F1. But F2 was P2 times A, that is pressure at the bottom times the cross-sectional area, minus pressure at the top minus the cross-sectional area, which was the same as cross-sectional area times difference in pressure, as we have already mentioned earlier on. And therefore, we also saw that the upthrust is equal to, if you bring in the pressure P2 and P1, of course, we know that P2 is density times G times H2 times A, and P1 is density times G times H1 times A. Of course, H1 is this height here, and H2 is the whole of this. So the difference between H2 minus H1 is just H. So the upthrust is equal to rho A rho G times H2 minus H1, which was the same as this quantity here that we have already seen. And of course, we know the volume of a cylinder is cross-sectional area times the height. So the volume of the cylinder is cross-sectional area times the change in height. Remember, change in height is just simply going to be H. So what does that mean? If I take this and this, cross-sectional area times change in height, that is the volume of the cylinder, which is going to be V. So the volume of the cylinder, therefore, is equal to the volume of the liquid which it displaces. Volume of the cylinder is going to be the same as the volume of the liquid which the cylinder displaces. So what does that mean? It means that the upthrust H is going to be equal to the density, because cross-sectional area times delta H is V. So the upthrust becomes density times G times V. So the upthrust will be the density times V times G. And of course, we know that density times volume is mass. The volume of the cylinder is the same as the volume of the liquid it displaces. So upthrust is going to be the density times the volume of the density of the liquid times the volume of the liquid, which is the same as the volume of the cylinder. This would be the same as the mass of the liquid times the density, times G, because the density of the liquid times the volume of the liquid is the same as the mass of the liquid. If I take the mass of the liquid times G, I get the weight of the liquid. So the upthrust is the same as the weight of the liquid which an object displaces. And by the way, this is what we call Archimedes principle or Archimedes principle. So if we are told to state Archimedes principle, therefore we shall just simply say the upthrust acting on a body in a fluid is equal to the weight of the fluid that it displaces. The upthrust of a body immersed in a fluid, or the upthrust acting on a body in a fluid, is equal to the weight of the fluid it displaces. So upthrust equals to the weight of the liquid displaced, or upthrust equals to the weight of the fluid displaced. That is Archimedes' principle. So you should be able to arrive at Archimedes' principle either mathematically or by just being able to state Archimedes' principle. The upthrust acting on a body is equal to the weight of the fluid it displaces. That is Archimedes' principle on of an object which is immersed in a fluid or in a liquid, to be specific in that case. Okay, so having explored Archimedes' principle, we now remind ourselves of floating and sinking that we mentioned in IGCSE. When does an object float and when does an object sink? So if the weight of an object is greater than the upthrust, the object will go down. It means the object will completely sink to the bottom of the liquid. if the upthrust is equal to the weight of the object, many times the object floats. If you just put an object on the surface of the liquid, it starts sinking. That means its upthrust starts increasing. If by any chance the upthrust balances the weight of the liquid, it stops sinking. It stops there. So if the upthrust is equal to the weight of the object of an object, then the object will remain in equilibrium and float. So this is what I'm talking about in this case. So if the weight is greater than the upthrust, the object starts sinking. But if the weight is equal to the upthrust, the object will just float. So when you immerse an object, it starts sinking to a certain depth. When it reaches a point where the upthrust is equal to the weight, it stops sinking and therefore it floats. If the weight is much bigger than the upthrust, then the object now just moves to the bottom of the liquid. That is what we are going to call sinking. So we now know the impact of upthrust. It makes the weight of the object to be smaller because the pressure at the bottom of the object is greater than the pressure on top of the object. And the difference in pressure results into a difference in force. So the resultant force on the object will act upwards, which is going to be the upthrust. Remember, I'm saying when the object is just placed on the surface of the liquid, it starts sinking, its upthrust increases. If the object is fully submerged into the liquid, the upthrust now remains constant because the difference in pressure will remain constant because it will depend now on the height of the object. To sum up this, I've given you a self-check to think about it, or to think about. A thin horizontal plate of area 0.36 meters squared is beneath the surface of a liquid of density 930 kilograms. The force on the one side of the plate due to the pressure of the liquid is 290 newtons. What is the depth of the plate beneath the surface of the liquid? So here they have given you force and they have given density, they want depth. So pressure due to the liquid will not be dependent on the area. So what is the depth of the plate beneath the surface? So you have two ways of thinking about this. Pressure is equal to force over area, which is the same as density times G times depth. So you have two ways of thinking about this. So this means you can say 290 divided by the area, which is 0.36, is going to be equal to 930 times G, which is 9.81 times the depth. So you should be able to find the depth. I'll just check with my calculator. 290 divided by 0.36 divided by 930 times 9.81. So this is giving me 0.088 meters. Avoid writing answers to less than two significant figures. A cube of side 0.2 meters means the area is going to be 0.2 power 3. Floats in water with 0.15 meters below the surface of the water. So what is submerged is 0.15 meters. The density of water is 1000 kilograms. Calculate the pressure to the water that acts upwards on the bottom surface of the cube and the force upwards on the cube caused by the pressure. So not all the 0.2 is fully submerged. It's only 0.15. So I know many of you cannot calculate this. So if this is the cube, not all of it is submerged. Just a small amount, just part of it is submerged. And what is submerged is 0.15. So it means the depth is going to be 0.15. But of course, the cross-sectional area is going to be 0.2 times 0.2 because the cross-sectional area is the base, which is submerged. So the depth is 0.15. It is not going to be 0.2. And the cross-sectional area is going to be 0.2 times 0.2. So calculate the pressure due to the water that acts upwards on the bottom surface of the cube. So the pressure is going to be density times G times H, which would be 1000 times 9.81 times 0.15. So that is the pressure. So 1000 times 9.81 times 0.15. So the pressure is 1470 pascals. That is the pressure to three significant figures. And then the force. Capture the pressure to the water that acts upwards on the bottom surface of the cube. So the depth is 0.15, not 0.2. And the force upwards on the cube caused by this pressure. So we know force is going to be pressure times the area. So the pressure is 1470. The area is going to be 0.2 squared because it is 0.2 by 0.2. So this is going to be equal to times 0.2 times 0.2, which is 58.9. I'm getting 58. Okay, 58.8, depending on how you round off this. 1470 times 0.2 times 0.2. 58.8 newtons. I think that is correct. A metal block of mass 0.6 has dimensions 0.05 by 0.04 by 0.03. That gives you volume. The block is hung from a Newton meter. What is the reading on the Newton meter when the block is fully submerged in a liquid of density 1200 kilograms? So it has dimensions 0.05 by 0.04 by 0.03. So we can say that this is length, width, and this is the depth. So what is the reading on the Newton meter when the block is fully submerged in a liquid of okay. So when an object is fully submerged, upthrust is the apparent loss in weight, and we said upthrust is equal to cross-sectional area times difference in pressure. We said upthrust is equal to density times volume times G, or mass of the liquid displaced times G, or density times the volume of the liquid displaced. So this could be equal to the upthrust here is going to be equal to density is 1200. The volume is going to be 0. What is the volume? I'll just multiply this 0.05 times 0.404 times 0.03. So this is 0.00006. That is the volume. Then times 9.81. So I'll multiply times 9.81 times 1200. So the upthrust is actually 7.06 Newton. So that is the upthrust. But remember, the upthrust is the difference in the weight in the liquid minus the weight when the object is fully submerged. That is the upthrust. So that means if upthrust equals the weight in air minus the weight in the liquid, we want the weight in the liquid. So the weight in the liquid is going to be the weight in air minus the upthrust. So the weight in the liquid is going to be the weight in air. The weight in air is mg, which is 0.6 times 9.81. So the weight in air is 5.9. Or 5, I'll write two significant figures, 5.89, three significant figures, newtons. That is the weight in air, that is mg. So I'll say weight in the liquid is 5, sorry about that. The weight in air is 5.89 minus the upthrust, which is 7.06. So minus 7.06. Am I doing the right math? Sorry, this one is 0. This was 0.706. I think this was an error. It is 0.706. So this is 0.706. Okay. So I'm subtracting 5.89 minus the answer. I think that is 5.2. So I first found the upthrust, and we said upthrust is equal to the difference in the weight in air minus the weight in the liquid. So I just made the weight in the liquid the subject. So the weight in the liquid will be the weight in the air minus the upthrust. That's why I'm getting 5.2. You can also try it and see. A balloon of volume 300 per meters cubed is filled with hydrogen of density 0.09. The mass of the fabric is 100 kilograms. Capture the greatest mass that the balloon can lift in air of density 1.2 kilograms per meters cubed. So they have given you a balloon of volume. This is the volume. It is filled with hydrogen of this density. And the mass of the fabric of the balloon is 100 kilograms. So that will give us the weight. Capture the greatest mass that the balloon can lift in air of density 1.2 kilograms. I think you should be able to solve this. So the upthrust on the balloon, just to give you a hint, the upthrust on the balloon will be equal to the density of air times the volume of the balloon times g. That is the upthrust. But remember, the upthrust on the object is equal to the weight of the liquid of the fluid it displaces. It is equal to the weight of the fluid it displaces. And remember, a submerged object displaces its own weight. So this is going to be equal to m times g, where m is going to be the greatest mass that the balloon can lift. So rho is the density in air, v is the volume of the balloon, so g will cancel. So it is just density in air times the volume of the balloon. So that will be, I think it will give you about 3,600, I think. You can verify that. Describe how to use a Newton meter, micrometer, screw gauge, a metal cube of side approximately 1 centimeter, and a beaker of water to show approximately that Archimedes principle is correct. The density of water is known to be 1,000. So you can try to relate to what we have just studied to describe that. Of course, remember, you have to find the weight in air and you find the weight in water. Then you try to subtract and see if the weight in air minus the weight in the liquid is the same as the weight of the liquid which is displaced. Of course, the weight of the liquid displaced is the density of the liquid times the volume times g. A boat has a uniform cross-sectional area of density at the waterline of 750 meters squared. 15 cars of average mass 1,200 kilograms are driven on board. So there are 15. Total mass is going to be this times 15. Calculate the extra depth that the boat sinks in water of density. So they have given us the density as this. So they have given us, this is the cross-sectional area. So we shall say pressure is force over area is going to be equal to density times g times h. So we have the total force, which is 1,200 times 15, that is the mass, times G. So 1,015 times 1,200 times 9.81, that is G, that is the weight, divided by the area, which is 750, should be equal to the density, which is 1,000 times G, which is 9.81, then times H. So this one cancels. You should be able to find the H. I think I will check my calculator what H should be. 15 times 1,200 divided by 750 divided by 1,000. I think it's approximately 0.024. 15 times 1,200, then divide by 750, divide by 1,000. So I think your value of H will be approximately 0.024 meters. You can try that and verify. So these are self-check questions, so I just gave you a hint. You are supposed to be able to answer them. I think that is the end of lesson 1. Until next time, do not forget to watch the solved past paper questions to get more confidence. Bye bye.